This one, I mean. So this data preprocessing, I have given all the clues for a sample data, taken up and all the preprocessing steps which are crucial being implemented over there. Right. So I'm sharing this link here once again. Otherwise, you'll get that same in the drive, which you already referred to.
This is for today's session, right?
No, this was for the previous session. You remember I mentioned that I'll be sharing a notebook with respect to the treatment regarding missing values, one-hot encoder, standard scaler, even KNN inputer, and let's say given
Okay.
smart.
I don't remember whether we have discussed this in our previous call, but I think you have explicitly shared it, right?
So
That
it
mode
carries,
and
yeah, it
noise.
carries, let's say, data which has to be converted into categorical and numerical columns first. Train test flag to be implemented. Pre-processing pipeline I've created. So the pipeline is a function which you can use in scikit-learn. This can wrap multiple steps. Like say, first step is impute, second is step is encode, and you can get those encoding for the categorical variables. No worries. I think in the end I'll again go through this if not understanding. But this was the data which has more categorical features, right? So how do we deal with them? How do we do the one hot encode and all? So a sample notebook I've created and served the same thing, guys. Sharing this right away so that you can take this as a reference. And if somebody require a discussion, in the end we can see.
My point is that we have not discussed this entire notebook in last call, if I'm not wrong, or have we discussed,
No, we had discussed all the functionalities for data
but not
pre-processing,
this notebook.
but like, yeah, not this problem.
Last one was more theoretical, I believe, for those what we have discussed. I think this is more like a practical sort of a thing what you have implemented, right?
So you need to be me to discuss that, right?
Yeah. So maybe we can start with this practical description. That's what my call, Dr. Ravi. If everybody agrees to that, maybe we can start
Yeah,
with
let's have a call for.
implementing that further. Yeah.
No, I agree. If we want to discuss something from the previous session, it should be in the start rather than in the end.
Never mind. So definitely, yes, I can do that. Just check you have the access, but don't change anything. Don't run that notebook because then it will crash from my side. So I've shared. But are you aware what we have discussed at least, right? On the pre-processing the theoretical conceptual framework. Please confirm. For that, at least you should be aware that we had discussed multiple steps in pre-processing. I discussed standard scaler. I discussed how do we identify the missing values, how do we check on the data's normalities, outliers, whatnot. So please confirm, guys. I mean, I should not get into the theory again. Please confirm.
Yeah. So on the high level, yes, it's there, but maybe this practical
The only thing
implementation
is that
will
if you use them, I think
bring
will
it
take
more.
at least 1.5 hours on the same. So it is like again going back to the basics.
No, no, I'm not sure.
Hmm.
Some theoretical part is there. We can correlate it with the practical implementation.
Okay, let me see what exactly are the queries coming in. But don't put in the feedback that it's something out of syllabus and deviated from the session. That's actually we are keeping a quick wrap up around what we have discussed the last time with respect to a given use case. Okay, the data preprocessing. All right, so let me begin with a very basic requirement. I need to have imbalanced learn library, which is handling the uh, you know the imbalanced classes, especially it is to be utilized when you have categorical variable, the target variable, which is categorical in nature. At the same time, one class is having more observations, the other class is not having that much observations. If you remember, I have discussed something on a fraud detection, and let's say 99 cases are there which are non-fraud customers, and only one candidate is there on fraudulent practice. So that is a very big imbalance. I have 99 categorical variables or 99 observations which are categorical in nature in the non-fraud cases. Only one is a fraud case. So how a machine learning model can build up? That's very critical. So I discussed that we implement a smart, and for that smart we need a imbalance learn or INB learn kind of a library. You have the notebook, so at a later stage you can run that. But the first priority is to get the libraries available. Once I get that library installed, what I do is, and this hyphen q is nothing else but keeping it quiet so that you don't see, that there is multiple output coming in. Just keep it quiet and clean. Second is I have imported multiple libraries, NumPy, Pandas. Scikit-learn has open data sets. So data set is having fetch, open, ML kind of a data set. Okay. That's the open data set available. I'll discuss that. What is the data? Then we are using model selection. Anybody, why do we need model selection for any library, for any model? What do we do with model selection?
Mostly, most of the methods is straight split, so making
Yeah.
the
So
fit among the data.
when I have data, I have to split that into target variables and not only target, but let's say the independent variables, target variables to be divided into two parts, training and testing, right? So we have train test split methodology where we apply this on my X variable and Y variable. X is nothing else but all the independent variables on which the model is built up. Y is nothing else but the target variable which I'm going to predict or detect or classify. So stratified k-fold is nothing else but a sampling technique. So we can divide the data into multiple samples as well. Okay. If you remember, we have cross validation as well. I have discussed. So k-fold cross validation is also a technique just to split the data into multiple parts so that we can check the accuracy of the model picking up random samples, right? So maybe some of the biasness could be there. To remove that biasness, let's pick the random samples and associate them and then see overall accuracy with respect to each sample that I discussed long time back, if you remember. Then I need standard scaler and min max scaler. Anybody? This you have to tell me why exactly we need standard scaler or min max scaler. This I have discussed at length, right? I think 1 hour we have spent on this.
Standard scalar is just to make the values in a definite range. So let's say if values are like 6,000, so we can limit it to a very particular range so that
Right.
our model is correct.
And min max is leveraging the values in a range of 0 to 1 only, right? So it was having that formula, right? You can see the formula that is x minus x minimum divided by x maximum minus x minimum, right? And then we get these standard and scaled values for min max scaler. Similarly, robust scaler I have not discussed last time. Robust scaler is nothing else. Here we are taking up minimum values. Here we are taking up average. In robust scaler, we take the median values. Okay. And we should be agnostic. We are not sure whether robust scaler is going to be helpful, when max scaler is going to be helpful, standard scaler is going to be helpful. We just can choose either of this and see what is the impact on my model performance. It's again iterative and experimental process. Am I clear? Robust scalar is what? Robust scalar formula, if you see, it basically is nothing else but x minus x median value divided by IQR, interquartile range, Q3 minus Q1. Okay. All right, guys. Please say yes or no. So I'm good. You are good. Shall I annotate it? The formula for robust scalar. So this robust scalar, if you see, you can Google it. It's nothing else but let's say I have x variable. I'll subtract a median of x and will divide by interquartile range, which is Q3 minus Q1, where Q3 is what? If you remember, Q3 is the n into, let's say, 3n by 4, right? If it's a odd number, odd series, it's 3n plus 1 divided by 4. And Q1 is nothing else but it is n by 4 or n plus 1 by 4 in case if the values are odd. And what is median? Median is nothing else, it is n by 2 or n plus 1 by 2 if the values are, the observations are odd. Please confirm. Can I go ahead? You got the understanding on what is the calculation which we do for getting a variable tuned as per robust scalar. Min-max scalar was x minus x minimum value divided by x maximum value minus x minimum value. Standard scalar was x minus x bar, the average divided by standard deviation. All these are meant to just scale the data in such a way that we get the normalized values. Still, I didn't get yes, so I'll again speak out. Please confirm. Am I clear now?
Yes, Ravi.
Okay. So now let's see how programmatically we can implement. And there is something known as quantile transformer. Okay. Right. So quantile transformer is nothing else but the name suggests that I can divide data into multiple parts known as quantiles. Okay. If I divide the data into 4 parts, it's something known as quartiles, right? If I divide into n parts, it could be a quantile. Now, quantiles basically is what? Quantile transformation is what? We are actually transforming this with respect to the, I should say, scaling functionality. Again, a type of transformation, again, a type of scaling the data so that we can standardize it. And that's how exactly we used to work out. Okay. And there are multiple ways of transformation. So there is a power transformation, which takes the nth root of the data and then taking the distribution. So that's basically nothing else but it helps me to again scale my data in a proper way. That's it. Any doubts so far?
Well, the only thing is we'll wait for that. So, for what kind of data, what kind of scalar or transformer we should be using, I hope you'll be covering that.
Sorry, can you come in? Which data and which scalar is it?
No. I mean, for yeah, no. I mean, there are different ways we could scale or transform the data. For specific kind of data, what transformer or scalar to use is something I'm hoping you will cover below. Like
So,
when to use quantile transformer versus power transformer, that kind of a thing.
all right, okay. So you need to understand that cheat sheet where exactly when to use different types of transformers, right?
Yeah.
Let's say this first one you are clear. When we have something in its range of minus infinite to plus infinite, the continuous data set is there. So this is going to be helpful. Where I have something when my data set is less, for example, like I don't have multiple variables, right? Uh, I just keep the data in the range of 0 to 1 so that I'm working on some probabilistic models. So this X minimum and maximum kind of model, min-max scalar is basically worked out. Ideally, this can be used for any data where you just want to scale the data between in the range of 0 to 1. Okay, so that's open-ended. There is nothing logic behind that. I just need my variables, my computation to be less, and therefore I need to keep the values between 0 to 1. It's more of a percentage kind of a data I want to create instead of keeping a standard scalar. When it comes to something on a robust scalar, so when your data contains outliers actually, because robust scalar is what? It is dealing with the interquartile range. So if the data is having more outliers, okay, the box plot, and if you see the outliers, there are huge outliers, then transform them using this. It's like a transformation happening with respect to the outliers. Mani, you got it? Till this three all clear, when to use what kind of a scalar?
That's fine. I think I got the outlier stuff. You use a quantile transformer and the power transformer both you use for outliers.
Exactly. Yeah. So if there are more rigorous, there are, let's say there is data which is something in a polynomial format, or which is in the format of, let's say, a square, something is like a cube and all. So in that case, you can use the power transformer, when this kind of polynomial variability is there. But when the data is having a few outliers, you can go and check with basic the robust scalar. Quantile transformer, when exactly we have huge number of variables which are actually, let's say in this robust scalar, you can see that there are few variables having outliers. In quantile, almost every variable has the outliers. So it is more aggressively having outliers. So it's better to use a quantile transformer in that case.
Okay. So just another question around outliers. So should we eliminate the outliers, or if the data is so discrete, then we
No, no.
transform them?
This is like, there are some use cases where you want to keep the outliers when
Okay.
you're studying the data, something like a COVID interface, right? In that case, what happens is when the COVID period is there, there are outliers obviously, but you need to understand the seasonality of the data and how exactly this new normal is basically derived. So in that case, you need to keep outliers. But something which is not a usual criterion, it is basically only a few observations, or let's say few seasons are observing some outliers, maybe because of some certain reasons, that you keep them agnostic. In that case, you can even transform the outliers. You take the log values. That's it. So there is a mechanism by which you can test it. Keep the outlier and see the model performance. Remove the outlier, see the model performance. Money, it is always going to be iterative. It's not that one model, one process, and I get the final crux. It is purely experimental EDA, because model experimentation is also a, what I should say, it's iterative in nature. So there is nothing which is static here. Everything is dynamic, and there is no one route to get the best model. Only in the deep learning you can avoid all this basic pre-processing. You don't care whether data is in what format, whether it's like having outliers, blah blah blah. You are ignoring those steps. You're directly working on optimizing the weights. So that comes with a deep learning. But in machine learning, you have to do this all kind of tasks. So quantile transformer, again, I repeat, when your data set is going to have outliers, but the data is to be transformed into normality, or let's say something is non-normal data for me. I need to convert that into normality. You can use that quantile transformer. That is also additional case. Power transformer is that you have a polynomial data, but you want to make it normal. So again, use the power transformer. That's again to make it normal. So along with removal of outliers or transforming the outliers, there is one more case that you need data to be normality. So bringing to that normality will happen with a quantiler and a power transformer as well.
Got it. Thank you.
Okay. All right. One more last thing on power transformer, that there is a concept of heteroscedasticity. I am not taught yet because that comes under time series. So heteroscedasticity is nothing else but when you are dealing with multiple regressions. When it is a time series data, what happens is that the error is not constant always. So if you plot the error of a model, it is non-normal. Okay. So if the error is non-normal distributed, in that case, it is heteroscedasticity. And in that case, power transformer is utilized to make it homoscedastic. Homoscedastic means the error plot would be normally distributed like that. Okay. So that's something deeper. So let's see how exactly we are going ahead further, and we can do that feature engineering accordingly. See, that's what I said, discussing every aspect again will be taking its own time. But anyways, I think it's good to go ahead. Can I go ahead further? Please confirm this. I'm yet to get.
Yes, Ravi, we can go ahead.
Okay. Hey guys, so annotation is done now. Removal is also there. Now you see there is one more thing which I'm doing here. I'm using multiple sorts of encoding. Okay. So what is encoding? Anybody?
I'm just converting some form of data into another form, so simpler form.
Mostly for enums.
Let's say I have got something like sorry, data like I have gender category. So gender is like zero, sorry, male, female. Okay. Another observation is male, then female. So these are categorical variables, right? It has, but this data is categorical, but also it is ordinal, isn't it? One could be multiple classes, but something could be very much ordinal, that is binomial or something. So in that case, you can see that encoding is to be leveraged. What encoding does? Male is zero, female is one. Male is zero, female is let's say one. So this encoding is done. So we can assign certain values and we can encode that data accordingly. Now you can see there is something known as label encoding. Okay, label encoder. Label encoder is basically suitable for a ordinal data where there is a perfect order between the data. Let's say high, medium, and low. You can see this ordinal data again, and it has it's on labels, fixed labels. Let's say there are different types of tsunamis, type 1, type 2, type 3. So this is something which is categorical, but there could be a number of classes. We have fixed a number of classes. Then we can deal with label encoders. That basically assigns the values accordingly. And one hot encoding is better for a nominal data. Nominal data, basically, you can see that it is basically either having the nominal values. We have certain names of people. We have certain categories of people like, you know, uh, the region-wise data sets, Asian, Hispanic, and Black, and whatever. So like that, you can, work out. Label encoding is, I again repeat, it's good when we have data in certain labels, low, medium, high, day 1, 2, 3, like that. When it comes to one-hot encoding, it is basically useful when we have certain nominal data sets, like color of a flower or something. It could be color of your cars or features of a car. So in that case, 0, 1, 2, 3 can be attached accordingly. And next is target encoding. So we can also have target encoding or ordinal encodings, multiple types of encodings. So this is basically again, I can show you the data and then we can go ahead further that how I am using the same types of different types of encoding for the similar data set and what is the difference over there. Next item is the imputation. What is imputation? What do you mean by imputation? It's like filling up the missing values. So for example, there is a missing value, right? So let's say I have gender. So gender is what? Male, female, male, female, like that. Suppose that this value is missing. This is blank by default, by mistake, whatever. Tell me what I can do in this kind of case. It's a categorical data. So how should I fix up that? Why? What should be this value? This should be male or a female. How I decide? Tell me. When categorical data is there, we actually take the frequency, okay, or mode. So if we see that most of the cases are male, so definitely with this missing value should be male. Okay. One is that remove missing values. Okay. Second is that fill those missing values. If you remove it, remove if the observations are less. But if 90% values are missing, obviously in that case it is very difficult. Okay. So we have to see what kind of data I'm having, how many missing values are there. And then it is again a judgmental thing. I will not be imposing anything here. You have to again check the performance of the model. Scenarios would be different. So you have to again try and test with what kind of values and treating missing values, what impact is there on the model. If you say you are removing the missing values, how many observations are left? If maximum observations are getting deleted, it is always better to treat the missing values. when I'm filling the missing values, the number one case is categorical data. If data is categorical in nature, we have to take the frequency of the data, like which observations are more, and fill that with that. It's basically replacement with a mode. The other replacement could be with an average. The other replacement could be with a median. The other replacement could be with a nearest neighbor. Okay, so multiple techniques are there. K nearest neighbor is using the nearest neighbor observation and then fill that. So it's I'm not yet taught you KNN algorithm, so we'll not discuss too much on that. Let's focus on simple embedder. When I discuss the K nearest neighbors and all these algorithms, I'll help you out further. Then for a decomposition for principal component analysis being implemented, please tell me why it is that. Why a PCA is implemented in any of the pre-processing?
Consolidating a few labels,
Sorry.
consolidating or reducing the number of variables.
Exactly. Consolidation, the right word is like clubbing up the, or let's say grouping up the particular factors, right? Similar variables which are under having better correlation with each other and all. So reducing the dimensions. Dimensionality reduction is the right workaround. Why do we implement the PCA? To reduce the multiple dimensionality of the data. So we get the less dimensions. Okay. Why pipeline is utilized? Pipeline is utilized for creating a pipeline like architecture so that in one go I can have multiple steps and I can see all things are implemented one by one within that pipeline. It just to ease out the process, nothing more than that. In feature selection, select the best F classification based output or chi-square based output. So these are like multiple things which we do when I have to use the best features. Okay. So let's say there are 500, 10 to 15 features which are impacting my, let's say the fraudulent customers. So I'll see that what are the best features which I should keep, what are the least significant features which I can avoid. So feature selection can be implemented. I'll show you that. All right, rest of the things are like a column transformer. So you can implement the whatever you have selected in the pipeline to the columns which are attached universally. And you can also use that column transformer to implement the same function on multiple columns at one go. You can also have a logistic regression classification report. This basically for evaluation of a module to work out on that. Very quickly, I have to remove that one. See, that's what like even discussing any notebook will be taking its own time to discuss what are the things which are happening there. But anyways, let's go ahead forward.
Dr. Ravi, will you be sharing this URL with us for the collab?
Arun, you have to be loud. Please, can you come again?
It's already being shared onto the chat.
Yeah.
Okay, I joined late, so I haven't.
Okay, somebody, if you can reshare, that would be
Yeah,
great.
please. That will be great. Thank you.
One last thing is that I have done here, there are random undersampler, SMOT, ADASIN, random oversampler. So these are nothing else but the technique which I discussed last time, synthetic minority oversampling technique. So whatever the number of observations are there in categorical variable, which are less, I can improve, I can increase the number of features, sorry, not features, increase the number of observations for that class. What I do, oversampling is done uh, when I have to increase the minority class. Undersampling can be done when I have to reduce the majority class. So 99 customers are non-fraudulent customers. So I can do a undersampling for those. And oversampling can be done for one particular customer, which is fraudulent customer. So I increase that numbers. Simple. And because IMB learn we are using to classify, to segment this or to have better sampling or to increase the categories. We can also use it some pipeline to implement all this multiple samplers together and see the performance at one go. As I mentioned that we have a data which is basically open source data. I think I have to import this libraries. Once it is imported, I can do that. And then I rerun that. All right, so let's see the data now. What is my data? So df dot head I will implement. So this is what data you see. There is age of people, working class, whether they are working in private, local government offices, or NN is what? Missing values, right? Not a number. It's a missing value. We have their weights. Basically, we have education. We have their, uh, let's say, marital status, occupation, relationship, gender details, their capital gain, their capital loss, the working hours per week, native of a country, and what is this less than or equal to 50,000 is nothing else but their income. So this particular person, 0th person, is having income less than 50,000. This is having greater than 50,000. This person is having greater than 50,000. So there are two classes, less than or equal to 50,000 or greater than 50,000. So what are the factors which impact their income? We need to test that. So target variable is this class, right? So whether the relationship, their occupation, uh, let's say their race, what is their the impact on that? And let me also check few more variables. So I have to go to this data, uh, salary data tag less than equal to 50K. Adult income data sets. So let me define you all the variables properly. So we are all on same page. All right, guys. So what is the data here? So we have 16 columns in the data. There is target variable, which is income, divided into two classes, less than equal to 50 and more than 50. There are different 14 attributes, which are actually demographic features to describe a person. Let's see what they have. This I need to check. Final weight is what I just want to understand that. Maybe they have described it here. Okay. Final weight in this case is going to be so it's a census measure, and as per it, basically it's nothing else but it's giving us the final weightage only. That final weight is that same. It is representing the number of individuals that a particular census record is meant to represent within that given data set. So let's see if how it looks like. Okay, so for a given observation of age, total these many people are there, where age is defined, this many people are there with final weights. So if I come back to my notebook, I have 226,000, right? 89,814. Bit confusing here. So this target, this variable, if you see, as per census, shows me the total numbers, right? Isn't it? Let me also trace it out. Apart from that, the capital gain, capital loss, all these things are actually clear. So if this final weight, if it is going to be around, let's say 1,000, okay, when I'm saying that this final weight is 1000, it means that this given respondent represent 1000 similar people in that same category of demographic. Okay. So this person whose age is this, right? 25 years of age, work class is private, all rest of the variables like that. He is resembling with 226,802 people in US census, as per US census. Is the information clear now? Please confirm. Is the variable clear?
Yes, sir.
Yes, yes.
Moving ahead, since we are now aware on different sorts of variables, let's see what all the things which are impacting their salaries. Okay. We have certain missing values, right? So I have a data frame, and let's say so you can see that when I say is missing value or is not a number, so wherever you get true, that would be basically what? That would be basically a missing value. So let's say here it is true. Okay. So like that, what I'm doing is, since my data is having missing values, I'm simply writing a function known as drop NA. Drop all the NAs over there. Now, if I again check the same observations, right? Df dot is NA. So now I'll see that there is false altogether. And we can also count the numbers. That's another thing. So we have cleared all the missing values. If missing values are there, no model is going to work out. So the first thing is that wherever you see the missing values, just use a function drop NA and clean those missing values. After that, there is another treatment also you can give in some certain scenarios. We'll see that also, that how do we replace missing values, right? So that is a one-to-one variable check and then case. Okay, so I'll discuss that also separately. As of now, I've deleted all the missing values. I'm dropping the last target variable while creating my X variable, or let's say series of X variables. Why? Anybody?
Maybe Dr. Ravi, before that, when we are saying we are dropping the NA values, does
Yeah.
that mean that we are reducing the number of rows or we are treating the NA in a different?
No, it's basically missing all the observations which are actually having the missing values, they're getting dropped. So it's that the treatment happening on a given row.
But for few data set that might not be true. The reason being dropping an entire row for having one NA value. Uh, I'm not sure whether it's true for each and every data set.
No. So here there are two things. If you see there, we have missing value removal, which we can do on an observation. We can also drop them column wise. So when I'm saying drop NA here, it's basically a global scenario which works on rows and columns both. Otherwise, you can also say that axis equals to 0, axis equals to 1. In that case, what happens is it can either get deleted from the given column, or the column gets deleted, or the rows get deleted. Maximum times, what we do is we treat the rows or the observations because that particular person is having missing values. So that's what we are removing. Okay.
Okay.
But what we can do is we can also say fill NA. Fill NA means what? If there is any missing value, fill NA. Fill NA with what? We can take an average, mode, or the frequency, or the median, whatever. I'll discuss that also. Don't worry. So my question is now is that when I'm creating a target, the independent variables X, why I'm dropping class here? So you can see that data frame is there. From there, I'm dropping a class item. Axis means what? Are you taking row or a column? Axis equals to 1 means I'm taking a column, considering a column. Okay. 0 means row. So I'm taking that column class and dropping that from my data frame, making it to X. What happens there? practically.
Except that column, all the remaining columns will be treated as X.
Right, Dilesh. So it's only taking the last column, which is dropping. Rest of the columns are still there. And then that is defined as X. So X is nothing else here, independent variables. What is Y? The target variable. So I'm again looping here. df within that, take the class and consider this as Y. That is target variable. So let me show you. If you see now X dot head. Oh, that's small X, right? I have
Right.
not run.
It's a big X. You have to.
It's big X, but I have not run that actually.
Okay.
Sorry. So if you see this, the X is nothing else but all the variables except the last variable. So till native country, I'm having the data set, right? What is removed? So this target variable class is removed. What is the target variable now? Kept it separate. So equation is built up. Y is equals to x1, x2, blah, 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 with their multiplication with the coefficients. So y is nothing else but a small y, I guess, right? So y is the last variable, the target point. And see what I'm going to treat, how I'm going to treat that. So now I'm seeing there are categorical columns in my data set. So select the data types, which are including categories. Select that and convert that to a kind of a list. There is a numerical column. Select those numerical columns and convert that to a list. What will happen is we can see that the basically categorical columns and numerical columns. Let me run that and show you. Then I'll again discuss the code. So cat underscore, sorry for that. So I have cat underscore calls, right? Category columns. So I have created a list of category columns: work class, education, marital status, occupation, relationship, race, gender, and native country. These are all my categorical columns. Very simple step to identify which are categorical columns. And similarly, numerical columns. What I've done is I have created a list of numerical columns. What I've used, I have used a function. The function is from X, select D types, data types, where the data is included as a float, that is decimal, or an integer 64, that is integer. And all those columns are selected and convert to a list. Similarly, let's see what are the numerical columns. So A is final weight, education number, numerical value, then capital gain, capital loss, hours per week are numerical. Hence proved, right? You have categorical columns are this and these are numerical columns.
Sorry, Doctor, we just can highlight. This workspace is not yet saved. So maybe we do lots of things and then try to save. Can you try to resolve this one? It's like
Okay, you need the rationale behind that.
no. I'm saying your workspace is not getting saved so far.
I'm not able to hear you clearly. There is some muffling.
What you are,
I'm
the purpose
workspace
On
is
the
not
top,
getting saved.
you have saving failed since 7:36 p.m. So he's saying your workspace is full.
Oh, okay. Sorry. So okay, no worries. So And in that case, right, train test split. Very quickly, please confirm that. Why do we do that? What happens actually behind the scenes?
The same X is being converted into multiple parts. One is for training part and one is for testing part.
Right. So we have X train, X test, Y train, and Y test. Don't change the order because it understands in the same way, right? First will be always X train, second will be always X test, second, third would be always Y train, and fourth observation would be always Y test. Implement this train test split on X data and Y data. This is my capital X, all data of X, all data Y. Stratify Y. Stratify is nothing else but a sampling technique, right? You are creating these data or groups, random stratified sampling would be there. So it just to be agnostic. If you remove it, that is also okay. That's nothing because by default it's always random. And how we are making it random from where 40-second observation is picked first to begin with the data. So whatever data is it is there. First observation will be 40-second, and after that it would be random. So if you want to assign it, you can assign. If you don't assign, that is also not making a huge difference because by default it's random. Test size is 20%, which means training size is 80%. So 80 training and 20 testing. Here you have to define what testing size in the argument. Next, this I'm discussing first time. So we can use the pipeline function from scikit-learn. This pipeline is nothing else, but we can have multiple steps which can be routed. So you can see I'm having a simple imputer. Simple imputer is that strategy is most frequent. What does that mean? The mode part, right? Whatever the categories we have, whatever is occurrence of a particular data multiple times, I can use that particular imputation accordingly, right? One hot encoder is basically used here. Handle unknown is basically ignored, which means that basically if there is something which is a category unknown, it should be ignored in that case. It is basically 0, 1, 2, 3, like that kind of it. One hot encoding. So I'm not doing anything. I'm just only creating a pipeline as of now. Okay, let's see where we are implementing the pipeline. This is a categorical pipeline, guys. So I'll be implementing it on what? In what series of data? Please confirm. The most frequent observations in the categories would be selected for categorical variables. It's a categorical pipeline. Second pipeline is for numerical data, So I'll be implementing that on numerical data sets. So there is a k nearest neighbor kind of a method. I can select nearby 3 neighbors and it will take another 20-30 minutes. So I'm sorry. I'll discuss it next time. But in short, if you need to understand, it's just nothing else but assigning.
One doubt. When you say pipeline means it is like building the model for that numerical features and categories.
No, it is data pre-processing pipeline. If you can see, it is nothing with a model, right? It is just only a pre-processing pipeline. So pipeline is nothing else. I can have multiple steps which can be performed in a single function at one go on my numerical data or categorical data. So otherwise, you have to do it one by one.
Like it is automated processing. Like when you select one function, it will automatically select. For example, here you are doing impute.
Right.
What exactly it will do? Like see, we are removing non values by normally. That to this pipeline, what difference it makes actually?
Okay, let me show you then what exactly it does. Okay, so suppose there is a missing value. Let me talk about this imputer, right? Simple imputer for categorical variable. I have male, second value is missing, then a female, then a male, then a female, then a male, then a male. So this missing value, which is having most frequent is what? If you count upon it. So males are how many? 1, 2, 3, and 4. What are female numbers? 1 and 2. So by default, this missing value, which is here, will be always considered to be a male category. Why? Because this is most frequently occurring. So the data will be having missing values, and in that case, it will be attaching this missing value as male for those variables which are categorical in nature.
So, Dr. Ravi, we have seen that we have already handled this drop NA stuff. Like we are already dropping the missing value.
Yeah, don't get confused.
That imputation
in the previous
will not
step,
come into the picture.
Let me tell you. In the previous step, I have dropped the NA, so no need to implement after that. I'll be doing is I'll be reinserting the same data frame, and on that I can
Okay.
attach these particular categorical and numerical pipelines. So please don't get confused. Yeah. So first I said this is the first treatment, that drop in a. Otherwise, you can again bring back your data frame, the original data frame, and implement on the categorical variable, numerical variable, these particular imputations.
That means, Doctor, if I understand correctly, there is no need to use the drop NA function in general. We can directly implement the pipelines with relevant algorithm. Is it correct?
Exactly. So if you say you don't drop NA, in that case you have to treat this NA. Otherwise, this will not be numeric data. It will be having something string like NaN. So it will not process your data. It will give you the error.
Okay. Once
So to
once
do
we
that,
build
there are only two options: either drop NA or treat NA. Okay, fill in.
okay,
So how do I
but
fill? I can go with a simple imputer for categorical variable, this strategy. For a numerical variable, this could be a strategy. Or it can be not only KNN imputer, it could be just average. You can also replace by the average values or median
so
values.
okay. So for categorical data, that impute is one function, and the next one is encode. What is encode? We'll do here encode
Okay.
and scale.
This is encode, which is basically now if I say I have data like male, female, this is string. So how a model will work, right? It won't work. So it will assign a value 0 by default to this F1. Whatever comes first is 0. Whatever the observation comes next would be 1 by default. So this encoding is nothing else but converting a string into a numeric value. 0, 1, right? Getting it?
This is clear. And what about scale here at the bottom? Scale
Okay.
in the
Scalar, you remember we have already used. This will be treating the numeric values could be multiple digits. So it will just take x minus x bar divided by standard deviation. And this formula will be implemented on the every variable so that they are having same scale. You know,
understood. Okay, understood. Clear.
but this will be implemented on numerical pipeline and data. This will be implemented on the categorical data. So you have to separate
One,
that one.
yeah, one more question. Like when we implement these pipelines, okay, so we are treating the NA. So after that, do you need to remember that what all we treated as NA and how their implication on the model output? Somewhere we need to note them, or how generally it is considered actually.
No, I didn't get you clearly. So you say that
So,
I am
for
implementing this
example,
pipeline. Yeah.
yeah, I am treating all the NA values, okay, with some
Yeah.
kind of algorithm, whatever we mentioned here, like
Okay.
impute and encode or impute and scale, okay.
Okay.
Now my data is completely free of NA. All are
Right.
filled with the relevant values.
Some values here.
Yeah, some values. Now I will get now I will be considering these pipelines for the model building.
Yeah. Only consider this pipeline. Otherwise, the previous data frame, if you pick, either it is dropping all the NS, your data set is less, and second, it was not treating the NS. So then also it will not work. So you have to use this pipeline further for developing a model. We'll see those steps next. Right. Are you getting how do we pre-process? And let me show you what is KNN imputer. Okay, in a very short manner. Okay. So how we are taking the k nearest neighbors. So understand that there is a data observations, right? Let me show you. Suppose there are two variables, okay, x1 and x2, and the observations are like that, right? So what you can see is that when the observations are very much random and if you study the correlations and all between these two, or one could be target variable also, right? So accordingly, what you are getting is you are seeing randomly you are picking a particular observation. Identify what are the nearest neighbors. So these are three nearest neighbors. Let's say this is the observation. So this is first neighbor, this second neighbor, this third neighbor. Why so? Because I'm only picking three neighbors. And take that average of these three values and fill that missing value with these three neighbors. So this is, let's say, missing value. I'll pick up the average of three nearest neighbors for this. And how this distance is calculated? This is calculated by Pythagorean equation, Euclidean distance. So let's say this is one observation, there's one observation, there's one observation. So this is how exactly you can see that I can build a triangle, and this becomes what? This becomes my hypotenuse, and this becomes, let's say, my opposite side. This becomes my adjacent side. So h square is nothing else but, let's say, o square plus a square. So this distance is nothing else but, let's say this is x1, this is x2, or this x3. So x2 minus x1 is a, okay? And you can then say that you can take the square of it. And this is nothing else but x2, x3 minus x2. So take the square of it. And then h could be nothing else but under root of it. So this is how exactly you can calculate the distance between observations. So basis that distance, you'll find that which are the nearest neighbors, three nearest neighbors. Take the average of that and fill with this average value the missing value, which is this one. Now getting. And let's assume that the value of this is 20, this is 22, this is 24. So then we are only taking three nearest neighbors and their average only to fill that. So the average is around 22, so you will fill that with 22, missing value. In short. Can I go ahead?
So the values may be integers and the resultant value we may get maybe floating value, right? So that kind
Yeah,
of
that's what we have taken. Numerical columns or pipeline is nothing else, but it is either a float or it could be an integer, anything.
Yeah, I mean, just trying to confirm. So mix of integers and float data is okay.
It could be.
Okay.
Because you know that first of all, if you see this, I'm very much focused on single variable. So if I distribute that against target variable y, so it's the same variable for. So if it is like a float, it's a float. I can have a separate plot for x2 because every treatment will happen independently. Here only for a correlation, I just mentioned that. But ideally, it will be what? It will be y and this variable, right? So accordingly, you can see that as well. So it will be the same class.
So is it a continuous? There are two types, right? Whether it could be discrete or continuous. So since this is a regression, how we are
See,
handling?
again, when it's a discrete, it's something which could be a categorical data as well, right? So
Okay.
it goes up. When it's a continuous, it comes here. And in
Okay.
continuous also, you can see that if it's a numeric value, because see, one hot encoder is also making it discrete. 0, 1, 2, that's a discrete data. So that would be this case. Numerical values are minus infinite to plus infinite. It could be integer, it could be a fraction, it could be anything, but should be numeric.
Okay. So the ultimate goal is to pre-process everything, right? Like,
Right. It's basically pre-processing notebook only. If you see the entire notebook title also, it's that only. That's it. All right. Can I go ahead?
Okay.
This is hectic actually. This annotation is basically really hectic for us. Isn't it? So now see, there is column transformer. I mentioned that you can implement anything, any functionality easily on all the columns with a column transformer. So what we are doing is we are saying that there is a preprocessor now. Okay, guys, preprocessor, which has column transformer function, which is now including categorical column and numeric column. In categorical column, you are going to implement categorical pipeline with categorical columns. You are having numerical pipelines with numerical columns. So that transformation will happen. Combining both pipelines using column transformer. So why column transformer is required? I have numerical pipeline, I have a categorical pipeline, and I have which variables? I have numerical columns, I have categorical columns, which are defined here. So on these columns, what I'm going to do is I'm going to create a preprocessor. So the preprocessor number one is cat, second is num. This cat works on categorical pipeline with categorical columns. Num basically is a preprocessor which works on numerical pipeline with numerical columns. Now see what I'm doing. Sorry, I have to run this. Now what you can do is, there is a model pipeline now which you can create. Okay. And this what we are using is, we are using now IAM balanced or IMB libraries pipeline mechanism, which will be integrating pre-processing, scikit-learn model, and SMOT. SMOT is what? Identifying, or let's say replacing those values or increasing those values which are minority by either increasing the minority classes or decreasing the majority classes or increasing and decreasing blah blah blah. So it can be done in multiple ways. Okay. So let's see how exactly I'm creating a pipeline. So it's a model pipeline. So this is IMB pipeline. This library is what? IMB, imbalanced learn. Okay, scikit-learn has imbalanced learn. What is imbalanced learn? This is just to treat those target variables. Let me show you here. Suppose my data is having y. This is only majorly for y, right? Suppose my data set is, what is that? Target y. So let's say all the values are 0, 0, 0, 0, 0. Only one value is 1. So what you can see is, this 0 is what? Less than equals to 50. 1 is greater than 50. So you can see that maximum observations are for those people whose income is less. So how do I create a model and which can be really impactful for predicting this category when it would be 1? So what I can do is, I have how many observations? 1, 2, 3, 4, 5. 5 is to 1. Like 5 observations are there for my 0 class and only 1 observation is there for my 1 class. So in that case, what I can do is, I can increase this last observation, entire observation, say multiply with 5. Okay. So it is oversampling. So 5 observations with 0. And let's say I have 5 observations which are 1 now. So it's balanced. You can decide the ratio. It's up to us. Okay. So right now what we are doing is, we are just by default using the SMOT. Okay, but why do we do that? Any idea? I have explained by the way why balancing is required, or somehow my oversampling is required.
To handle with the minorities.
Right. So the data would be, if you now build any model, it will always predict something as 0. It will never ever predict 1 because there are only less cases. So just to improve our number of cases, we are simply replicating the same value. So I have what? I have something known as preprocessor here. IMB pipeline is nothing else but the pipeline similar to what we have created as a preprocessor pipeline. This has, we need to write steps is equals to step number 1, preprocess, apply preprocessor. You see that I have created one preprocessor above. Use second as balance. Balance is nothing else. Use a function SMOT, and random state is the same 42. Upside we have mentioned that. There is a classifier. Classifier is my model. So use logistic regression, and number of iterations, multiple types of iterations could be 1000. You can even leave it blank. You don't want to give that define that. It's by default, it could be n number of iterations. So that also you can do. What happens is, as of now, my data set is is free of missing values, right? So imputer processor will be not making significant things because already it will be having no missing values, right? If it is missing, then only it makes sense.
Dr. Ravi, sorry to interrupt. Can you please clarify one more time the random state 42 and the
Okay,
balance?
random state is nothing else. If you see, there is something known as, okay, I'll show you. Random number generator. Okay. So what is random number generator is doing? I'll show you. So let's say I have minimum value of my observations is 1. I have maximum observations 10,000. When I click this, it will randomly generate some 3694. Okay. So this could be my seed. Seed is what? First value which you want to pick is 3694th observation. After that, you can pick everything randomly. It could be then 4,000, it could be 7,000, it could be 8,000, anything, isn't it? It just
But
random
it won't
selection.
select the already selected ones, that observation. That will be taken care by the model.
Even
So
if you
that
don't select, it doesn't make any sense. It is just only, to start somewhere. What will happen is if you don't select random number is the moment you run your model one time, okay? So the observations which you are testing upon, those will be randomly selected. So somehow the results will not be same. Every time iterations will be different. So accuracies will be different. To fix up that thing with every iteration, accuracy also is almost same. So in that case, you are fixing up the random seed. Are you getting it? Because every time iterations will be different, probabilities will be different, iterations and experiments would be different. So you can get some different training samples and testing samples. So the accuracies would be slightly up or down like that. To fix that, we say that, okay, fix it at 42. So which means that now I'm going to have sorted observations. Every time when I rerun, it's going to observe the same kind of randomness with multiple times of rerunning the things. Retraining also is.
No, this random number generator is clear, but what is signify that 42? Is it like you will select the
It
42nd
is just
number?
whatever the observations are there, start with 42. Simple. I randomly selected that. It could be one also. You can say two also.
That means select the 42 observations, then you start the process.
I'm not
Is it
saying
so?
42 observation. It is 42nd observation. So your data of customers is having customer ID 1 to 100. So 42nd customer becomes your first observation to begin with. And then the random process starts.
Okay.
Okay.
And the balance, there is one more mentioned about balancing. So the balancing is for a target variable.
Balancing always check for target variables. So independent variables could be imbalanced, but don't worry about that. It's okay. But when the target variable is imbalanced, which is going to be impacting, because most of the cases are like one class. So it will predict by default that class only. It will be biased model. So avoid that biasness. Let's increase the number of observations of similar classes, minority classes. Only that is the hack. There is no other hack.
No, but increase observations, you need to add them, or the model itself will include them automatically when we
No,
say
it will increase the observations first. Then only the model will start working. Okay.
So one doubt.
Yeah.
Sir, actually, for now, suppose if here we are using a smart actually, so basically we are doing a oversampling actually. So,
Right.
but so suppose
What is it is synthetic minority oversampling technique.
okay, so is it like we should first check whether we should go for oversampling or undersampling by checking the I mean the outcome.
That's that also you can do. You can have that's what I've kept under sampler over sampler also separate in when I bring that pipeline. So that also we can do. See, it is all iterative process. You can try any AI, right? You can directly implement a smart, or you can first check the undersample over sample what is to be done. But it is very critical because see, uh, it is all depending on accuracy. You are not sure whether undersampling will help or oversampling will help, or treating both also will be helping. Can I say beforehand? No, it's not. So by default, you start anything randomly, you can start. There is no
experimenting
step.
actually. It's more of experimenting.
This purely experimentation.
Okay. Thank you, sir.
So once I create this model pipeline, I can then train a model. So earlier we used to see model is equals to logistic regression. After that, what we do is model.fit. Same we are doing here. Model pipeline.fit function is utilized and model is fitted on training dataset, X train and Y train. Same, only pipeline is built now, which includes processors, which includes balancing algorithm, it includes classifier model. And what is happening in this? Pipeline is created, column transformer is used for implementing categorical and numerical columns together. In categorical, this is happening. In numerical, this is happening. And on both, all overall data, smart is happening. And then logistic regression is happening, guys.
Dr. Ravi, one
It's
question.
not as a random state of 42. Sorry.
It's very basic question. Like I just want to understand, like when we say these are all pre-processing step, is there any criterion or something where we decide like whether we have to execute maximum number of pre-processing step. Like you see the data, it is more like
It's again, honestly, it's experimental. So it depends how much time you have, effort you have to treat that particular, pre-processing. So I can spend 5 days on pre-processing only, isn't it? So I can go deeper, 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 deeper like that. It all depends, has to be done with respect to optimization. You have to see, we need to be cognizant about time, money, and efforts and utility,
so
right?
there is no specific guideline. It is as per
There is
your
nothing. There is nothing
situational.
strategic. It's purely you have multiple types of pre-process available.
Yeah.
Handle with care. More you
Okay,
dig,
so you
more.
can randomize it. You can just pick some, or if you have time or whatever, you
Yeah.
can just involve as many as possible.
Because
Okay.
if you don't have time at all, go for a deep learning based mechanism if it is having highly complex data, right?
Understood.
So which
Thank you.
doesn't take care of all these preprocessors. Why I'm dealing with this preprocessor? Because I'm using scikit-learn packets. I'm using machine learning approach. Go to deep learning neural network. Don't require anything like this.
Perfect. Thanks. Thanks.
Yeah.
And Ravi, another question.
Yeah, man.
Does this pre-processing vary between a classifier model versus a regression
Nothing.
model?
No. It's nothing to do.
Same.
Preprocessor is preprocessor. It's like pre-processing before model building. So nothing dependent over there.
Okay.
It's a model agnostic tool.
And another naive question here. So, like, let's say whatever you have done here in terms of pre-processing, can I use it as a template for everything that I do?
You can, but there are let's say some of the steps which you can further do, right? Outlier checks and all which are downside. But yeah, you can use this as a template.
Okay.
So at least you get some template, to start with fixing up something.
Okay. And I don't see you doing a PCA on this. Isn't it a necessary
No,
step?
not necessary because see, I have let's say a very handful of variables, right? So I thought that I'll take a data which with large columns, but it would be so much complex, and already we did that PCA earlier. So that's why I wrote it. But I have given you the hints. What all things you do in pre-processing with this when you implement these libraries. So you can keep it next level. Okay.
Sounds good. Thank you.
Yeah. It's like cumulative thing for you. You can also see the other aspects. What you do is don't drop in it. Use the imputers directly on the data frame. Okay. So that also you can do. So what is the next thing? I have implemented a model with model.fit function, model pipeline.fit function, and it implements all this pipeline. Then further what you can do is, okay, instead of now predicting, I have given you some more clues to work on exploratory data analysis with charting and all, right? So this is my shape of the data, like 45,000 observations almost and 15 columns. Okay. You can also check the basic descriptors, what we do always. Why you're seeing not a number? Because what I've taken up, I have taken up the original DF again here. Okay. While processing. And missing value per column also you can see now. If you see the DF which I have is null, you will see that there are 0 columns now with null values. And this NaN basically is what? Can somebody tell me? This marital status. So it doesn't have standard deviation, it doesn't have minimum value, it doesn't have the 25 percentile and all. It's a non-numeric variable, it's a categorical variable. Therefore, you can see that NA. What you can do, you can use Seaborn now, Matplotlib for charting and visualizations. So what I'm doing is I'm creating a count plot. Count plot is created on data frame to see the number of classes. Okay, class distribution. We are seeing that imbalanced data is there. So let's see. So how many cases are less than 50,000? We have almost around 34,000 plus, right? How many cases are greater than 50,000? We have 10,000 plus kind of cases which are more than 10,000. So there's a class distribution. This is imbalanced thing, right? So what happens in SMOT? This category and this category could be equal, or slightly you can increase it, slightly you can decrease it. This is when you are decreasing it, it is undersampling. When you are increasing it is oversampling. Then in the next pipeline, in the next charting, what I've done is I have created, selected the categorical data sets. Okay. Select data set, data types as category, say include equals to category. Uh, Check that list of categorical variables. Now for every column in categorical columns, create a plot of a dimension 8 by 4. Get me the count plot for every variable of the data frame because it's column, right? It's every column in the categorical columns. And keep the title, text, title layout, etc. so that you can see this in a better way. It's just to visualize every categorical variable. So when I'm seeing the charts on categorical variables, let me start with the first categorical variable. Class. Class is less than, yeah.
One request. In above you have shown the imbalance. Na? Do you have any output after the smart technique? How that imbalance will reduce? Any chart can you show if possible?
Which chart? I'm sorry.
The one you shown the class distribution. You have mentioned
Yeah,
that.
see, that is implemented on the model, but here I'm taking the same data frame. So I'm not saved that output to data frame. You can see that I have just only fitted a model directly. I have not saved that in my original data frame. My original data frame is same only. Getting it?
Understood. Maybe toward
In
the
the
end, maybe
model pipeline, in the model pipeline that is implemented, but I'm not implemented that on my data frame again.
Okay, from the model, is it possible to plot that one here? We just want to get some visual feel, like how the smart has worked to bring that into contention.
Let me show you something like white. All right. So what you do is you have white train, right? You can see that I have taken what? I have taken up something known as count plot here.
Yes.
Here, right?
Yeah.
So data is equals to data frame. Now let's say it is Y capital or what? No, no, no. One problem is there because this count plot carries
Data frame.
the entire data frame, right? And this is now a single vector which I have. Okay, that's what. So here, if you see, my data is having class object that is having two items, which is basically greater than 50,000 and less than equals to 50,000. For that, I have taken the entire data frame. From that, I'm picking up the class. The problem is that. No, let me see a quick hack. But let me continue, and in the end, we can do that, right?
Sure,
Otherwise,
sure,
it will-
sure, sure, sure. It's fine, it's fine. Yes, yes.
Correct. So what happens is, but I'll show you. So what happens is like distribution of work class. If I see for every variable, let's say federal government, how many cases are there? Local government, how many cases are less than 50,000, more than 50,000? So I get a count plot for every variable which is categorical in nature, and I am defining them on a class. So class is this two only. How many cases are there in federal government which has less than 50, more than 50, less than 50, more than 50, like that? Similarly, distribution of class with respect to education. How many cases are there which has maximum income? So maximum income, if you see, it is happening with bachelors, some college, high school grade, graduation at least. If you see distribution by class with marital status, when people are married, CIV kind of spouse, they are having maximum income. When people are having what kind of profession is it? So this profession, executive, managerial, something like that, gives the maximum income. And next to that is professor or speciality, something like that, professional speciality. What is this? Occupation. So if a person is a husband, tends to, this is basically relationship, not occupation. Relationship, husband, if is there. So if a person is married, I think that's basically having more income. Husbands are earning more, I mean. Then comes race, white people are earning more as per the US Census records. If you go by gender, males are earning more. If you see like that, so native country, so obviously this data is again coming from, it's a world data, is it? Strange. Then you can then work out on float and integers and then see how exactly the histograms can be plotted. Histogram is basically nothing else but winning the data. So this is the distribution of your plot with respect to histograms, the frequencies of different age group, final weight. These are all numerical columns. So we cannot have the count plot. For this works the histograms. This is important. Last time I mentioned, you can also create box plots. So what I'm using for a box plot, I'm using all the columns in the function. SNS, C1 library has a box plot function, which is implemented on every column of the data frame. Okay. So you'll see that all the outliers are detected for every column. I'm not treating it right, but you can use my functions to create and treat that. You can also get the correlation. I have not taught you correlation, but yeah, let me show you how correlation works. Okay. What is this? Anybody aware on the correlation formula and all? How do we calculate correlation? Anybody? Anybody?
Pearson's correlation.
Sorry?
The Pearson's correlation.
Pearson correlation, right?
Yes.
Sure. Yeah. Let me show you the formula. So I was thinking today we'll go to the next level, but still we are reprocessing. But I think this is useful for you guys. Okay. Only looking for a feedback. Don't say that we are deviated. It's all agreed upon thing, right? These days I'm getting very good feed, you know. All right, guys. So let me tell you how do we manually calculate the correlation. So you can easily understand. So correlation is nothing else. It's relationship and it is between two variables. It's always between two variables. Don't say multiple correlation. Okay, multiple regression can be there, but correlation, because word co is there, it's always between two variables, variable 1 and variable 2. So let's say there is x1 and there is x2. Now this relationship could be a positive correlation. This could be a negative correlation. This could be zero correlation. Come what may, whatever the value of x2 is, x1 is always same. It's constant. So zero correlation. This is exactly 45-degree kind of reverse 45-degree. From here you can see it's like going to be negative correlation. It's a positive correlation. The range of correlation lies between -1 to +1. It is highly positive correlation and is highly negative correlation. Zero is no correlation. Next, how do we calculate correlation? So it's correlation, right? So which means that I have a formula where I have x minus x bar multiplied with y minus y bar, means another variable, divided by x minus x bar the whole square, the square root multiplied by, and summation of it, multiplied with square root of summation of y minus y bar the whole square. Or it's not y and y, you can say x1 and x2 instead of y, the whole square. It also has divide by n, but when we are actually taking this here and removing these things, so you can see that this gets removed, n is getting cancelled. So I need these values, okay? So let's say instead of x, y, I'll take x2. So let's say I have 1, 2, 3. Their other variable is 2, 4, 6. Let's find it. Is x1, This is x2. What I do is x minus x, x1 minus x1 bar, x2 minus, sorry, x1 minus, let me remove it, guys. I need more space. Are you able to follow me? You are able to listen me? Please confirm.
Yes, sir.
Yes,
Yes.
Ravi.
Okay. Again, let's have a quick check. X1, x2. Observation number 1 is 1, 2, and 3. This is 2, 4, and 6. So I need one column, x1, x1 minus x1 bar. Because this is minus, so I can avoid that sign. I can take square. Now I need x2 minus x2 bar, x2 minus x2 bar the whole square. What is the last column, guys? X1 minus x1 bar into y1 minus, sorry, x2 minus x2 bar. Okay, so what is the average? X bar, x1 bar is equals to 2 and this is equals to x2 bar average. So 1 minus 2 is minus 1, 0 and 1. 2 minus 4 is minus 2, 0 and 2. Sorry. My bad, guys. Where is my reason? Sorry. This is my eraser. What was the mistake? This is x1, xi1 minus x1 bar, the whole square. So this 1, 0 and 1. Similarly, x2 minus x2 bar is nothing else but minus 2, 0 and 2. When you square it, it is 4, 0 and 4. Multiply this with this. So this column, let's say column number 3 to be multiplied with column number 5. Okay, so there's 3 into 5. So 3 is minus 1 and minus 2, it's like 2. 0 into 0 is 0. 1 into 2 is 2. Take the total, it is 4. Now, what is the formula of correlation? So correlation, which is basically represented as R, is equals to summation of x1 minus x bar into x2 minus x2 bar divided by square root of x1 minus x1 bar the whole square, summation of it, multiplied with square root of x2 minus x2 bar the whole square, summation of it. So x1 minus x1, sorry, x1 minus x bar and x2 minus x2 bar, total is this. So numerator is what? 4. I get numerator as 4 divided by square root of x1 minus x1 bar the whole square and its total. So it is 2 and this is 8. So this is under root 2 multiplied with, let me remove this side, floating meter controls, multiplied with under root 8. So ideally, if you see now, it is 4 divided by root 16, which is 4 by 4, which is equals to plus positive correlation, significant 1. So what is correlation, guys? R equals to 1 here. 100% positive correlation. Any doubt? Please confirm. Audience?
It is clear, Dr. Ravi. It's clear.
It's clear, right? So the correlation is very simple. It's like I'm just taking up these values, right? If you do reverse, it will be minus. So reverse would be what? Let's say something like 6, 4, and 2. So in that case, you test it. So what will be the value? So this remains same. This remains same. Now 6 minus 4 is plus 2, and this is minus 2. And here it is like x2 minus x2 bar is like x2 is this. So this is also 4, the same 8. Now what I do is I have
I think your
X.
screen has frozen.
Sorry,
Okay. Your screen, the changes what you are doing, I think it's not visible.
is it?
Yeah, it's frozen. We are not able to see it here on whiteboard.
Let me reshare my screen. Now,
Can
please
you
continue.
try to write something on the whiteboard? Now we can see. Can you go ahead?
Yes,
Okay.
yes.
So no worries, like let's not do that much. So you can see that what we can do is we can have x1 and x2 and we can implement the same formula as per whatever the data comes in, right? So next step is that how what function we need to use. So let's say I have something known as uh, scipy.stats. So you can say from scipy.stats import Pearson R and imply this Pearson R on x1 and x2. That also you can do. Otherwise, we have correlation function. We can simply use data dot CORR. So this correlation is also useful. Either you can use SciPy package or you can use directly the dot correlation function. Okay, let's see what I have used here. So if you come back, can you see my notebook? Please confirm.
Yeah, we can see. Yes.
Yeah.
So what I have done is I have not only, okay, let me show you first of all, instead of plotting it, that I have data frame and I'm simply saying, oh, the problem is my data frame is what? It's mixed bag of all this numeric and category, right? So let me say new underscore false. And that's also a list. So I have to select by default. Or let me show you in a different way, just to see. Let's say I have A is equals to uh, numpy dot array of observations 1, 2, 3, 4, 5, and 10. And I have B equals to, let me hide, floating controls. B is equals to numpy dot array and something like 10, 8, 6, 4, 2, and 6. How many observations are there? Should be equal 1, 2, 3. I mean 5 and 6. This is 3 and 3, 6. Now what happens is like I have to create a I have already created one array. These are like two arrays. So what I need to do is I need to work out now in such a way that I have a data frame, right? So pt dot data frame, okay, and now you can see that if I create a correlation between variable a and b, which is 1, 2, 3, 4, 5, 10, b is equals to 10, 8, 6, 4, 2, 6, This is minus 44% kind of a correlation, negative correlation. Why so? Because if I see these values are increasing and these values are bit decreasing. And so if you see this calculated manually, you will get that value as minus 0.44. 0 and 0 is same variable, so it's one correlation. 0 and 1 it is like different, so it's minus 44. So same you'll find between 1 and 0 also same. Right? That's it. Everybody got it? Please continue. Okay. Similarly, now what we have done is we have created a heat map so that we can not only get the dot correlation values, which are annotated. Annotated true means this label you are getting with this annotation. Color map is this pool warm. This pattern of your heat map is known as pool warm. On what you are implementing correlation? On a heat map, which is having numerical columns. So I have a data frame which has numerical columns. Okay. And on that, I have implemented this correlation. So let's say we have a data frame and we have what in data frame? The numerical columns. And on that, if you select numerical columns, which are listed out there, and if you implement a correlation, so you get the correlation matrix for all these variables, which are numeric in nature. If you see categorical column, you will not get anything because they are categorical in nature. Right? But if they are imputed, okay, if they are imputed, in that case, you may get certain values. So here, most of the values are not imputed as of now. It's like on the model I have imputed. So therefore, you can see that it's considered as a string. The moment you impute them and then retry, then you can get the between 0, 1, 2, 1, 2, 3, 0, 1, 2, like that, you'll get certain values. So as of now, numeric columns are there where the correlation matters a lot. And last is that you can create a dot predict function. Dot predict function will get prediction for all the values of X test data. So there's like Y is equals to A plus B of X. You can also get the coefficient values. You can get the classification report and everything. This we have done the last thing. Same one. So what we have done, we have handled missing values, encoding is done, okay, scaling is done, SMOT is implemented, but on the model, integration is done with respect to multiple types of data pipelines, like preprocessor was implemented on categorical columns and numerical columns. Model was implemented as logistic regression and classification report is done. This is what I have shared with you guys, just to do the preprocessing, basic preprocessing. All clear? Any doubt?
Ravi, can you please explain that 0, 1, 1, 0 last one? Last example. Classification. Yeah, this one.
This classification report.
No, just below, which you explained as, I mean, little bit top. Yeah, this one.
Okay. So there's nothing else. Like I'll show you if I can annotate again. See what I've done is I have taken variable A and I have taken variable B. So what is A? A is like 1, 2, 3, 4, 5, and 10. What is B? So B is like reverse. So 10, 8, 6, 4, 2, 6, something like that, right? I think I again add 6, but it will not be 6. It is 4, 2, and again 6. So when, let's say, A is 1, B is 10. When A is 2, it is 8. When A is 2, let's say this is 8. When it is A is 3, it is 6. So when A is 3, it is 6. So like that, if you can see now it's showing a negative relationship, right? That's why it's a minus negative correlation. So one variable is increasing, the other variable is decreasing. So assume there are two stocks in a company, right? You have a stock of a umbrella manufacturing company. You have a stock of, let's say, what is that? Winter wear. Okay. So there are two companies, only two companies, right? So what happens is when the share price of umbrella will increase, do you see the winter wear also will increase? Isn't it?
Yeah.
It will not be that much because this one different season, this is a different season. Just hypothetically, I'm saying, right? So it will be a negative correlation. But you need to keep a stock of both sides because the moment when your umbrella is giving you the values, winter wear will not be giving. But when let's say something else happens, when this is increased, this will be decreased. So your portfolio get diversified. It's a risk diversification. So how you diversify risk? By keeping two stocks of negative correlations. One which moves with the market, one which goes down with the market. So when market is up, one share give you positive value, but other can give you the negative value. To meet that negativity, we can also have the positive. So it's always better to keep stocks of negative correlations than positive. Because if market goes up, stock one goes up, suppose second also goes up. But when market goes down, both stocks will be down. So that's why negative positivity is also checked. Okay.
Okay.
So with that comes an end. Let's take a break, guys, now, and I think then we can begin the regression part. Does that make sense? Let's have 15 minutes of a break.
Yeah.
Yeah. Let's have some water, some tea, coffee, whatever you prefer. Or meal can't be done in 15 minutes. It could be a quick meal. That's it. Hope the session is interesting, guys. You were enjoying the session.
Yes.
But now next level discussions would happen because we'll be starting now regression. And I'll be giving you much more quick hacks and things further. So let's wait. So what are the major aspect now we need to cover is the next module is we need to work out on regression models, right? I think I have already given you the basic workaround, manual workaround, programming workaround on regression. But still, we need to spare two modules entirely on regression. So I'll try to give maximum out of that, right? What are the quick aspects we need to work out? Supervised learning based workarounds and linear models. So when the data set is continuous, data set is labeled, supervised, how do we understand the input and output relationships? How do we get the best fit values of the models? We call it least square method or least square model. Uh, how do we deal with overfitting issues? How regularization is basically worked out? What are the L1, L2 regressors, regularization techniques which are there, which I discussed long time back manually. You'll also see the same programmatic. Any doubt in the topic of understanding that we are going to start regression family models, and that is linear regression. Please confirm. Any doubt? Anything we need to discuss? So let me begin with a simple linear regression model. Okay. This dates back to 1970s, where exactly there is classical linear regression model was defined. So classical linear regression model is having certain assumptions. Okay, guys? We need to prove and disprove those assumptions. There is simple linear regression, which means that I have two variables, let's say x and y. So y is equals to a plus b of x plus error. That's a straightforward model. Multiple regression is when I have y and it is like I have multiple variables, b1 x1 plus b2 x2 plus bn xn plus error. And there is last model which is polynomial. So this is polynomial regression. This is multiple regression. This is simple linear regression. In polynomial regression, what happens is that I can have relationships amongst the variables like x1 square, b2, x2 cube, like that, vn xn to the power of n plus l. So you can see that this relationships can be polynomial relationship. We can have exponential relationships, right? So basis this equation changes the model type. And what we need to do is we need to understand what is a classical linear regression model, assumption, hypothesis, and all part. So classical linear regression model is nothing else but the basic regression model, which says that for any model to be regressive model, one variable has to be independent variable at least, and one has to be a dependent variable. Dependent variable is also known as target variable, right? Or the predictor. Independent variable is basically nothing else but the x items, x1 to xn. We can have multiple independent variables on which target variable is dependent. Predictance, right? So the other assumption is that data should be normally distributed. To have a linear regression model implemented, the data, which is x and y, should be normally distributed. Okay, which means that when you plot this, every variable should be normal. There should be no autocorrelation. There should be no autoregression, right? So correlation I have shown you, but something is known as autocorrelation that you need to check. Regression I have discussed, but what is autoregression that you need to check? There has to be no multicollinearity. Multicollinearity. I'll use my whiteboard then. Like that, there are multiple assumptions. So just to help you understand all these assumptions, and remember this very important discussion we are having, right? So most of the things I have not discussed earlier. Okay. This is not this. This is basically okay. So let me rewrite all the assumptions. Number one, there has to be one dependent variable plus one independent variable. Data should be normal distributed. There has to be no autocorrelation. There has to be no autoregression. There has to be no multicollinearity. There has to be no heteroscedasticity. Hetero, which I explained, right? Error distribution should be normal. Which means that errors should be normally distributed. It should not happen that today the model is giving 90% accuracy, tomorrow it gives 80% accuracy, then it gives 70% accuracy, then 45% accuracy, then again 100%. So it should be normally distributed on a daily basis, right? Right? These are the major assumptions which we need to check. So if there is, let's say, this should be the must, right? Dependent and independent variable. Data, if not normal, then the regression will not be classical linear regression model. It would be log normal regression. Okay. It can be also polynomial regression, right? autocorrelation. So I told you that autocorrelation is between x1 and x2. Sorry, correlation is between x1 and x2, two variables. What if the variable is nothing else but it's x1 or x at time t and x at time t minus 1? So today, let's say the stock price is 100 rupees. Tomorrow it is 115. Next day it is 118, 120. So this is also a data. This is time period t. But if you see the previous record, so previous value on this day, when the date is something today, let's say it's 10th, 11th, 12th, 13th, like that. So 9th, the stock price was 90. On 10th, the stock price was 100. On 11th, it was 115. On 12th, it was 120. So this t minus 1 is nothing else but lagged value of same variable. So if we are seeing, if we discuss correlation between same variable and its lagged value, there should be no correlation. It is known as autocorrelation. Correlation between a variable value at time period t with respect to variable's value at time t minus 1. There has to be no correlation among that. If there is a correlation, which means that there is a dependency also with the lagged values. So we can predict a stock price from previous days of a stock price. If that is the case, we need not require any other variable. So these kind of models are known as theoretic models. And when autocorrelation is present, you don't apply regression, you don't apply stats, you apply econometrics. Okay, slightly difficult to understand, I know that, but we don't apply statistical models. We then go to the next study, that is econometric modeling. I don't know if some of you have heard of models like ARIMA, auto-regressive integrated moving average, GARDS, generalized auto-regressive conditional heteroscedasticity.
So,
Vector
Ravi, this is also similar to time series, right?
Yeah, these are all going to be time series environmental studies, because the autocorrelation to check, we need lagged values. Lagged value means time series data. Getting it? Which means that if my data is having something autocorrelation, autoregression, it's not a cross-sectional data, it is a time series data. And therefore, I need to apply those family of models which are not cross-sectional family models. These are like time series models, which are econometric models. Now clear? Okay. So this school of thought is entirely different. I will not be discussing today these three category of models, but I'll make it sure that once we go to time series, I'll discuss that. So today we are going to see that autocorrelation should be absent. Autoregression means what? The y earlier we see is dependent on a plus b of x. In this autoregression case, what we see y is equals to a plus b of y at time t minus 1, lagged value of y. Getting it? Multicollinearity is nothing else but when x1 and x2 themselves are dependent on each other. It is multicollinearity. So let's say x1 is nothing else but a plus b of x2. So if we get these kind of equations and relationships, and they're sound correlated, so in that case, basically it is known as multicollinearity. So relationship between two independent variables, if that is established, this leads to multicollinearity. And what is heteroscedasticity? Heteroscedasticity is nothing else but if you have error plots, y predict minus y actual, if you plot it for 5 days, 10 days, if that distribution is not normally distributed, in that case, it is heteroscedastic data. Okay, the model is heteroscedastic. So basically, you need to work out on autocorrelation, autoregression, multicollinearity, and heteroscedasticity to make it classical linear regression model or simple linear regression model. To explain one more time multicollinearity, I'll give a simple example. Suppose that there is a pocket money of a person given by a father. So it's dependent on father's income. And suppose mother is a housewife, so dependent on mother's pocket money. So pocket money of a child is a function of father's income. Mother also keeps some pocket money and then gives the child pocket money. So he's also dependent on mother. This is nothing else but a constant which some amount he's always carrying. Maybe some earlier, some relative have given or something, whatever extraneously available beforehand. So constant. One day what happens is he got a bad relation with father. So father stopped giving money. Mother is actually dependent on father's income. So what will happen is even mother is blocked, which means that now we cannot predict pocket money of a child. Am I clear? Please continue. Mother's pocket money is by default dependent on father's income. So pocket money of a child, if it is considered, it is difficult now to predict because even father can ask mother not to give money. So there is a impact of one variable out here, which is impacting overall prediction of this variable. This is known as multicollinearity. Right? Where you can see the equation between these two also. So mother's pocket money is equals to a function of B1 times of father's income. Okay.
Dr. Ravi, one question.
Yeah.
So if these are present, we need to remove some variables to ensure that
Right.
these things are not being present. Is it so?
So we need to then check, let's delete mother's pocket money and then see the impact. Okay. Likewise. So you have to remove variables. There is now something known as variance inflation factor. Okay. Variance inflation factor, which should be around 1 to 2 or normal max to max 5 or something. If it is like 10, 20, like that, we directly see that there is multicollinearity happening. So just stay tuned. Like in coming sessions, I'll discuss all these facts, like how to check VIF values, how to design VIF factor, so that we get to know that multicollinearity is absent, autocorrelation is absent, right? So there are multiple tests. For autocorrelation, we have Box-Elgin test. For autoregression, we have um, a Dickey-Fuller test, like that. So we'll have certain tests, but not to confuse people and not to make it complex, avoiding that discussion. But are we clear? What is a linear regression? When y is equals to a plus b1 of x1 plus b2 of x2 plus b1 of x and plus error part. What is error? Y predict minus y actual. That is also present in the data as an error part. So let me tell you once again, b1 is nothing else but slope and it can be identified by equation. If it is between y and x1, it is x1 minus x1 average multiplied with y and y average, summation of that divided by summation of x1 minus x1 bar the whole square. That's it. So this gives the value of b1. Similar to correlation. In correlation, what is that? There is another variable also, y1 minus y1 bar the whole square. So we are not taking that part and we are not taking square root. It's just that we are taking this fraction. So I get a value of slope. And what is A? A is nothing else. Y average minus B into X average. Constant is constant. So it will always be same. So we know the Y average, we know X average from the data. Just we have to identify B, so we get the value of A also. So what do we do? To predict something of X item, we simply say Y predict is equals to a constant. Let's say it is 2 plus B1, let's say it is 3 point something, 3.5 multiplied with X1. X1, let's say it is 5. So we can predict that. This is what is prediction equation. And there is something known as root mean squared error. I already shown. It is nothing else but square root of summation of y predict minus y actual score square of it divided by total number of observations. As simple as that. Our objective is to make it almost zero. No error should be there, right? The unit of root mean squared error is nothing else but unit of y. So if y is in dollars, root mean squared error will be in dollars. If y is in weight as kilogram, root mean square error, if you see, its unit would be in kilogram. There is last thing, again a brush up, something known as R square. R square is nothing else but explanation power of your regression model, which is nothing else but 1 minus, you can see y minus y predict, or y predict minus y actual, the whole square, summation of it, divided by y actual minus y average, the whole square. It is actually nothing else but 1 minus this part, prediction minus actual, is nothing else but bias part. This is nothing else but variance part. So 1 minus bias divided by variance is your R square. Or you can see 1 minus error, because bias and variance are nothing else but the error part. So which is indirectly known as accuracy. So the explanation power is like, if the value of R square is 80%, so you can see that this model is actually able to explain the relationship between y and x as strong as 80%. Okay, so it is 80% more powerful model. 90% is better. 100% the best, but it is overfitted. Okay, that is most ideal. We can't get that. If we get that, we need to reduce that. Okay, guys. So if I'm getting 100% accuracy, I'll regularize it. So I have L1 and L2 kind of mechanisms to regularize it. I'll come to that discussion at a later stage. But let's see what we have in the agenda. So, okay, one last thing. How do we program it once again? So I'll have the first step is I'll define x. So x is nothing else but I'll use data frame dot drop y over there. So that becomes what? X. And y is nothing else but from the data frame take the y variable. Then what do? We then say x train, x test, y train, y test to be created. Okay, using what? Train, test, and split method on x data and y data. And then you can say test size is equals to some around 20%. So 80% is train. After that, you define a model. So model is equals to linear regression. Okay, this is a blank model, linear regression without any fine tuning. Base model, you can say. And then you use model dot fit applied on x train, comma y train. And then you predict. So y predict is equals to model dot predict on x test data. And how do we get the accuracies? We can simply say that from sklearn dot matrix import mean underscore squared underscore error. And this mean squared error will be implemented on y predict and y actual. And then you get the accuracy scores. I mean error scores. So 1 minus error is accuracy, like that. Isn't it that simple? Please confirm. Yes or no? Everybody got to remember the steps of any model, machine learning model. This could be linear regression, this could be support vector machine, this could be logistic regression. And then after that, we use dot fit. After that, we use dot predict. After that, we check the metrics or confusion matrix or root mean squared error, depending on the model. A yes or no would help. Am I audible?
Yes, doctor.
Yes.
All sorted? Yeah. Perfect. Seems to be. So let's come back and do some kind of checking on what else is there in these lists. So we train the model. The data is going to be house price data. Plot the line charts, like how the variables are related, correlated, which test the accuracy of the model. This is basically the uh, data which you are going to work out. Today I'm going to have index of the rows are 0, 1, 2, 3, 4. Area of a house, number of bedrooms, number of bathrooms, type of material, locality, and then we need to predict price. That's it. So let's have a notebook. And the notebook is here. Hide routing metal controls. Okay. So let's see how a linear regression is implemented on a house data. So where is the house data? I have to bring that back. Come up, come up, come up, come up. Connect, connect. And I'm uploading my database. This is a house.csv data. I'll show you the data also. What all libraries I require? Pandas for data manipulation, NumPy for arrays workarounds, scikit-learn linear regression, train test split, as I mentioned, scikit-learn.metrics has mean squared error and r square underscore error. That is r square values, right? So I'm using pd.read function to read that CSV, that is house.csv. I have area of a room, bedroom, number of bedrooms, number of bathrooms, material type, locality type, and price type. So we are going to have X as area, bedroom, bathroom, material, locality. Target variable will be price. So X is nothing else but, okay, let's say one single linear regression model, simple linear regression model I'm building. So I'm using only one variable, area and price. P is equals to, sorry, Y is equals to price, X is equals to area. So divide these variables into splitted values, right? So the same thing, train test split, test size is 25%. Whatever you want to keep it, you can have it 60%, 20%, 30%. Ideal is 70 to 90%. The training should be, and testing should be 30 to 10%.
Hi, Dr. Ravi. Can you come again with that 70 to 90, what you talked about? The training split?
Let me write it. What I'm saying is, like, ideally, by default, what people are doing is, so we have training data and we have testing data, right? So let's say I have 1, 2, 3, 4, 5 days of data. So this portion I'll be taking out of 3 out of 5, right? That much percentage I'm saying training. And this data I'll be using for back testing. So it is testing data, right? 2 out of 5. And this is 3 out of 5. So most oftenly what happens is training data should be around 70% to 90% people keep that in that range. And similarly, testing data set is 30% to 10%. So here you can see we are putting testing size is 25%. Means training would be 75% and testing is 25%. Now clear?
Okay. Okay. So what will be the ideal will be within this range that you talked about,
Nothing.
70 to 90?
It's all operation experiments.
Okay. Okay.
There is nothing ideal. Okay. Then, if you go further, you'll see that I have used the same model.fit. Model is defined as linear regression. Model.fit is equals to X train and Y train. Let me run that. Implemented linear regression. What is next step? Let's see regression line. Regression line is that always which I showcase, right? So for example, if I show you this, these are so many observations. This is X and this Y. So regression line is nothing else but that standard line which passes in between so that we can check the errors from this standard line versus the actual observations. Okay. So I'm having scatter plot on X train and Y train, sky blue color plot. Label is training data. I'm using model.predict. Are you getting it? Model.predict function to get the predicted values. And this is trained values of X. So this is Y predict versus X actual. Okay, that I'm doing. So similarly, you have a training data. All these blue values are actual data. Regression line is passing from the center almost. So what is the error here? This is an error. You can't predict it efficiently. You can't predict it. These values are correctly classified and predicted, which are on the line. So there is an error actually, right? So let's evaluate. I got a hack. So here what I'm doing is this. I'm saying that I'm using model.predict function again to get the Y predict values. So Y predict is always equals to model.predict. And it has to be always on training data, X-train. Okay, you can also use X-test by the way. So one you test it on train data and then apply on test data. Next is I said two things, R square and one is root mean squared error. Both are different. What is R square formula? 1 minus Y predict minus Y actual, the square of that divided by Y actual minus Y average and the square of that, summation of it. This is R square. What is root mean squared error? There's Y predict minus Y actual square divided by total number of observations, summation and square root of it. This is the error part. This is explainability part. So for a training data, R square is 32% only, very poor. And root mean squared error is 22,362. Huge error. So if you are predicting training data and price can be whatever your prediction for X value. It can be either plus or minus 22,000 units. So price of any variable, if you find any observation, it will be either plus or minus this much units, which is very weird. Total R square is for testing data 19%, which is again very poor. It should be ideally more than 70%. And see again the testing accuracies. So when you predict the price, it is plus or minus 22,219 units, up or down. So it's huge error for the model. Let's go ahead. Now let's say we are visualizing prediction on test data. Earlier it was of training data, right? Now testing data. Testing data is less obviously. It's 25%. Again, you'll see there are errors. Last part is you can see R square values, how they are being calculated, right? R square is nothing else but this is R2 underscore score function implemented on Y test and Y predict value, Y actual and Y predicted. Okay, that's one. So this is the symbol function from matrix packets. You can also get the coefficient values. Okay, so let me show you. So model dot coefficient, if you write, okay, what is that? My model name is model only, right? Let me check model name. right? So my model coefficient is what? 74 units. What is coefficient, guys? Slope, right? The B part. So which means that my model is like this. Y predict is equals to A I have not identified plus I have identified coefficient. Coefficient is what? 74 times of x1. X1 is what? Area. Let's identify constant also. Model dot intercept. So intercept is very huge, right? Constant is very huge here. So Y predicts is nothing else but constant, which is minus 18,984. Okay. Plus this multiply with area. So at any given point of time, let's say area is 2000. So 2000 multiplied with 74.92 plus minus of 18,984. This is my price of that particular house of 2000 square feet. Are we clear? Please confirm, guys. You got the equation.
Yeah. Okay.
You got R square for training. You can implement it for testing. You can get RMSE for training and for testing. Ideally, overfitting is there when your training accuracy is found to be more than testing accuracy. And underfitting is there if training accuracy is less than testing accuracy. Overfitting means that you are almost getting 100% accuracies, which is also not good. Underfitting is like 30% accuracies, 40% accuracies. There is no fixed limit. That's all for module number 13. I mean, week 13 kind of session. Let me show you the diagram.
Ravi, Dr. Ravi, sir, this collab that you showed us, will that be available with the?
Yeah, this session collab. So you have the access on both drive. I guess you have the drive access.
Yeah, I have that access. Yes.
Will be same note the backend. Okay.
Okay.
What is this? Let's see. Let's see. Let's wait. So this module was very fast, right? Because I think I have already discussed this manually multiple times, right? So I think you're all okay. Please confirm.
Dr. Ravi, like here we have tried to predict the cost based on one parameter, right? Like only on area.
Yeah,
If we have to do across
module
multiple features.
module 1. In
Yeah.
module 2, we'll conduct multiple reviews. It's a simple linear review.
Okay.
2 parameters. That's it. But I think my screen got freeze, guys. Okay. Please confirm, or you are able to see now. That's why it should be.
Yeah, it is visible now. Yeah.
Okay, so what we did is we had one variable here. Okay. So imported the required libraries, linear regression, train test split, mean squared error, R squared score. Okay. After that, we read the house price, use area as the input, predicted price. After that, we divided data into 2 parts, training and testing for X and Y. So 4 parts, 25% of the data was used for testing, 75% was training. Model was linear regression, model.fit was used for training a model. After that, we plotted the scatter plot to plot the regression line of training data. We got the accuracy check on training and testing data sets separately, R square and RMSE both. We got to have the plot for regression line on test data again. And we have predicted the value for testing data again. Predicted versus actual data on testing data was actually marked again. I also shown you how to get the R-square score, coefficient values, and intercept value for building the equation. And why use the linear regression? So in that case, when your data set relationships are not straight lines, then you go for non-linear models of flow. So linear regression need to be avoided. We'll then discuss non-linear polynomial kind of regressions. So how it looks like? Linear regression is like when your data is having a kind of a linear order of relationship. If data is like this, it's non-linear regression. Okay? When it happens, when there is up and down of relationship for same value. With seasonality, it happens majorly. So real life example is age versus income relationship. I mean, it could be anything, right? Regression can be used for anything. Then comes multiple linear regression. What is multiple linear regression? Again, I said, now we'll have multiple variables, P1, X1, P2, X2. Again. Okay, guys. So I have multiple coefficients, P1, B2, B3, and constant is only one. That's it, only the difference. Now let's have a multiple linear regression. Okay, let me have another one. So if you see now,
Sorry, Dr. Ravi, I just checked the drive access. It's not there.
no worries, I'll share the drive access.
All right. Thank you.
So if you see now, this is, I think this we complete, right? This is simple linear regression. Okay. Let's have multiple linear regression. For that also I need to have the data, and data is what? Again, the same house price data. What will be the change now? Anybody? What will be the change in this notebook? So instead of X, which was area, now it will be all variables. That's the only difference. Isn't it? Same libraries, same magic. Linear regression, train test split, R square, square, and mean squared error. Same data. But now, because we are going to deal with some more variables, like there are categorical variables also, we need to treat them. Coding should be there, encoding should be there. So there is direct function also, get dummies. Instead of one-hot encoding and all, you can also use pandas dot get dummies. It will directly create dummy variables. Means like material. Feedback is there. So material aspect will be divided into multiple things, right? 0, 1, 2, 3 like that. Reverse side will be 1, 2, 3 like that. Okay. So dummy variables are going to be created. Okay. One thing I'm going to avoid. Let's see if I don't drop first. This is the magic. Now you'll get multiple values actually. So if I don't drop first, you will see huge values. So material is concrete, 1. Material is masonry, 0. You get two variables for same variable. Getting it? You have one variable which is material concrete, Second variable additional added, material masonry. Instead of dealing it in same variable, it is dealing in two ways if you don't drop that. So for example, I have
Dr. Ravi, can you clarify one more time this one? That single variable, two variables.
I'm explaining with a simple example. Say there is a gender. It is male and female. Very simple, right? When I'm using get dummies function and not dropping any of the first values, what it does is this is going to create two variables, male and female, separate. Instead of one variable, it is dividing data into two variables. So if male is 0 here, obviously female is 1. If male is 1, obviously this is 0. Now clear? So the smart way is just take only one variable. Either take this variable or take this variable. That is also same. Why to have additional complexity? So we will be dropping this first
But
one.
if it's three categories, three
This
or
will
four categories.
no, so this will be another added like other. This will be two. Getting it? Okay. So it will be then ordinal in that case. So get dummies is used, but in that what we are saying is we'll be dropping first. So drop this, and in this locality also multiple localities are there. See, three localities, four localities, one, two, and three. So now there will be a difference. Now see the difference. So only one variable is deleted. Rest it is there, right? So first locality is dropped. The other two localities are present. First material is dropped. Second is present. Like that. Drop first equals to two. That's it. So this data frame encoded and encoded head is 5 observations. Then after that, what we do is on this data frame, which is encoded data frame, we are dropping price because that's a target variable. So making it X. Next is Y, which is target variable. Now all sync. Split data into train test split, ideal test size 25%, build a model linear regression, model.fit on train data, evaluate the model on train data, test data separately. Can you see now significantly if multiple regression is used, R square is increased like 80% and 77%. Means one area was not good to study. If I have multiple variables, it is better. R square improved and this also dropped. From 22,000, it is 50% at least. Okay, still it is another. It should not be more than 5, 6 units, 8 units, 10 units. Then again, plot this. I'm not discussing because you know that we are plotting only, nothing is specific. Then again, we create the coefficients. So to make it simple for you, let me show you in a simple way, right? So you can understand. Okay. So if I say now model dot coefficients, okay, and let me use a pandas data frame, pd dot data. Frame. So what do you see? This is coefficient number 1, coefficient number 2, coefficient number, four different variables, right? We have input variables. In this function, what I'm saying is I'm naming them. So I'm saying that coefficients are period data frame only, but give the names also. So x dot column is nothing else but name is attached. And give another variable that is coefficient, the value of coefficient as model code coefficients. That's it. That's how exactly you can see. This first feature is area, coefficient is this. Bedroom is this. Bathroom, coefficient is this. This is very problematic. Material masonry that has 17,000 kind of dependency. 35,000 of dependency on locality summary. Huge dependencies. That's it. Is that clear? Step 2 clear? Please continue. So multiple linear regression was implemented, right? Model training, model splitting, model evaluation, visualizing the predictions. And the last part is polynomial equation. When the relationship is like this. So as I mentioned, equation is now different. It is x square, x cube, x to the power of n. So it's known as polynomial equation. Simple. For same data, we can implement this, right? But how do we write that model? Let me show you. So whenever data is having a curved or non-linear relationship, polynomial is used. When underfitting is there, polynomial is used. When feature interaction need to be of higher order, we need to check that. We need to use polynomial. That's it. What are the advantages? It is easy to implement interpret, more flexible. There is no risk of overfitting. It requires feature scaling for stability. Feature scaling is what? Improvising the number of features, right? So features engineering is going to be better. Now let me show you how exactly we create a polynomial model. So, sorry. From scikit-learn.preprocessing, we have polynomial features. But model name is linear regression only. So from pre-processing perspective, we are saying polynomial features to be used. Otherwise, linear regression is used. Same model, but polynomial features. Rest things are, we just start to process polynomial features. How to create a polynomial feature? Take the square and degrees of that. So we can have a degrees of 2, 3, 4, multiple. So we are taking squared degrees. Polynomial dot fit underscore transform is implemented on train data. Polynomial dot transform is then fitted on test data. So X train and X test is created like that. No need to implement on Y. Polynomial variables are X variables. So train and test. Fit underscore transform and dot transform. Directly you can use that. What is poly? Poly is the polynomial features. Okay. This is how exactly we create polynomial data. Then fit a normal regression model. That's it. Then use the same dot predict function. Then root mean squared error, R square errors. That's it. Same thing. That's it. So very quickly going back to polynomial. So same data set guys. Only this is different polynomial features. Oh, one thing is missing, data. Yeah. So there are too many sessions, right? So taking the data again, yes. So where are the changes? So the first change is this. We are taking polynomial features. Okay. Apart from that, everything is same, almost same. Data is same. Dropping the columns, material and locality because they are categorical in nature. So polynomial regression won't be suitable for that. Numeric values are taken. So we have rest of the variables, number of rooms, bathrooms, area, etc., and price. Then also, only the thing is here you'll find a difference. Poly is polynomial features, decreases to the power of 2. Include a bias, avoid it, even if you keep it blank, it's okay. Then fit the model, fit underscore transform on extreme. Similarly, on xtest polynomial, use poly.transform only. Fit underscore transform on train data, but no need fit on testing, directly use transform.
Dr. Ravi, one question. Hello.
Yeah, go ahead.
So we are dropping the categorical data in case of a polynomial regression. Then how do we consider the effect of those parameters?
No, we don't consider them. No? So it's simple. In that case, those effectiveness we cannot check. It's purely for numeric data, right? It's x1, x square, x cube, x to the power 4, x to the power 4.
Okay. So that means when you do polynomial regression, if the data set has the categorical data, then
it is only
we
fit for
lose
majorly.
then eventually we may lose some accuracy due to ignoring those parameters.
We can't say that because I think that degree of relationship could be maintained here if these variables are prominent. So if we see that categorical variables were less significant, their coefficient value is like 0.000 something, by default we drop them.
No,
It's
but how
again,
do you test? We need to test them correct now. What is the influence of them having on this?
This purely intent trial because I had to show you one notebook. I am using that. It may be ideal, it may not be ideal, right? So it has multiple models you have to devise, and then only you take a call out.
No,
You
but
getting?
okay, this is clear. One question, like by assigning some numbers, so can we include the categorical data into this regression model, like by encoding them, then assigning them to here, or that won't work?
If I say 0 square, what it will do, right? Again, it will be 0. If I say 0 cube, it will be just waste of your data and observations. Because it will have 0 for sure, right? 0, 1, 2, 3. And 1 square is what? Again, it's 1. 1 cube is what? 1. So
Understood. Understood. Okay. The significance will come down drastically. Understood.
So as per the equation, highest power will be the first priority, right? Equation.
Yep.
And the constants you will neglect, right?
So here you see, when we are implementing it on a training data, always fit is used. For testing, only transform is used. Just check that. That's it. After that, it's all same. Linear regression, model.fit. But here, instead of training, it's extending polynomial. That's it. And when it is predicting, it's on xtrain and xtest predicting polynomial.
Okay.
Yeah. What is this? Okay, this is it. Then again, we are using what? Instead of using that r underscore square function and mean and squared error function, they are taking numpy dot square root. There is mean squared error also function. So we need a square root. So they have taken a square root also. The another way. Don't get confused. It's root mean squared error. So root and mean squared error. Adds a r2 underscore square. That's same r square. For training data and testing data, it's being calculated. And print results. Again, higher values of RMSE and poor values of R square, 46 and 40. Out of three models, I think second model was better. It was 80% R square. That's it, guys, for today. Any queries? Please come. Any queries?
Yeah, can you just give access to the drive?
All right. So, okay. Yeah. Let me remove this floating control. Sorry. Floating.
But even I don't have the access, so can you grant me the access?
Oh, I'm sharing. And for it, I'm having the sharing access also. So here, if you see, here's my sharing option. Putting that in the chat. Can you check you have the access now, please? If not, then we'll ask Ashwini to give you access. Please
Yes,
confirm
got
this.
the access. Yes, got the access.
Perfect.
Yeah, able to access.
Okay. Sure. So I think I am keeping everything there. So you can enjoy that. Perfect. Next time we come in and we discuss regression part 2, that is going to be further overfitting, underfitting issue handling. That's it. Now, I think sessions will be further smooth for you because I have multiple times deal with the same thing. And it would be like for next 5 sessions, it will be like support vector machine, logistic regression, linear regression, blah, blah, blah. That's it. Thanks so much. Enjoy yourself.